Okay. So good morning. Welcome. Oh, is it not morning? Nope. Well, hello. Welcome to our last week of lecture, really. So in this week, you will or have been looking at organic chemistry. Okay. So hopefully you have had a chance to attempt at the quiz before coming here today. Okay, so the first question, a big chunk of this material is naming it. There's a lot of it's a whole branch of chemistry that's different. So because it is very different, we will have to approach it um, very differently also. So you have to have new ways of naming things. So the first question here says, what is the name of the hydrocarbon with 9 carbons in a continuous chain? So 9 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So from the list of prefixes that you should remember, how would you say 9?
I don't
Non.
think one was on the list you gave.
Right, very good. It was non. And then we always ended, if it's a hydrocarbon, that means it only has C and H. That's what hydrocarbon means. It only has C and H, and so it looks exactly like that. So we just ended with the ending name of ANE. Okay, so that's the name. So that would be letter D, no name. Okay, so as a review, if it only has 1 carbon, we call methane. 2, ethane. 3, propane. 4 is butane. 5 is pentane. Starting at 5, it gets kind of easier because it goes with the root word, the Latin for the number, right? Pent is 5, so that's pentane. 6, Latin root for that is hex, so that's hexane. 7, heptane. 8, octane. So here 9 is no name, and then 10, of course, is decane. Okay, pause here for any questions on that.
What is the most we can get? How many carbons? Is 10 the most?
12, 10. Yeah, 10 is a lot already. I usually don't go above 10, but I think the textbook goes up to 12, so I'll go up to 12.
Okay.
Yep. For naming, of course. For properties of stuff, the chain can even be longer, and then but you just have to know the properties of it. For example, the longer the chain is, the more solid it is. So for example, methane is a gas, right? It has only 1 carbon. Then we go to octane, it becomes a liquid, right? The more carbons, the more electrons something has, the more London dispersion force it has. So the more intermolecular force. So from gas becoming liquid. And then when you go to like 15 and above or something like that of carbons, it becomes even a solid now. That's, for example, in the textbook, they give you, that's how, what's wax when you put on an apple in the grocery market, that's basically a hydrocarbon with a long chain. Yep, so that's a fundamental naming system there. Of course, I can go back to this if you have any more questions, but for now, let's move on to number 2. Number 2 asks, what is the correct formula for this compound? And really, what I'm trying to get at with this question is, do you understand what this structure represents, right? Because this is the first time maybe we are dealing with something called a bond line structure. Or in your textbook, they call it a skeletal structure. Okay, both of these mean the same thing. The fundamental part of it is that every straight line represents the connection between 2 carbons. So for example, there's a straight line here and a straight line here. So therefore, there's a carbon here and there's a carbon here. Okay, if you do that again, this segment here to this segment, that's another carbon, that's another carbon, and so on and so forth, right? Now, oh, also this is a carbon. If at the end of that line segment, something is written in there, then it is no longer a carbon. So for example, this chlorine is written on the top there. So this is actually not a carbon there. It just means that this carbon, let me highlight in different color here, that this carbon in green here is connected to a chlorine atom. Okay, so there is actually no carbon there. So because of that, how many carbons do we have? We have 1, 2, 3, 4, 5, 6, 7. So we say C7. Okay, that eliminates answers D and E already.
Can you count the 7 so that I could see?
Right, I highlighted it in blue and in green. So count all the dots I have highlighted. So 1, 2, 3, 4, 5, 6 blues, and then 1 green. So that's 7.
Oh, okay.
The reason I'm highlighting the green one is just to show you that that one's a little bit different because it's connected to a chlorine atom also. Okay. The next part of this question is for every carbon atoms, how many bonds will it have? Anyone remember what I said about that? For every carbon, how many more bonds will it have?
2.
Not 2.
Damn.
Every carbon will have 4 bonds. Okay. So for example, I'm gonna write it. So for example, you could be methane, so it has 4 bonds, 4 single bonds, right? Or if you think about carbon dioxide, notice that there's 4 lines still, right? So that rule is still good. Or when you think about formaldehyde, that carbon still has 4 bonds to it. And the reason why is it 4? Remember, each line represents 2 electrons. 2 electrons times 4 is 8. So it would follow the octet rule. So that's a rule that carbon will then always will follow too. Then it will always have 4 things, 4 bonds. Not necessarily 4 things, but 4 bonds. Okay, so for example, this one in the middle has 4 bonds and then 4 atoms in its connection. Whereas this one, because of that double bond, it has 4 lines, but only 3 atoms. And then this one, carbon dioxide, it has 4 lines, again representing 8 electrons, but only 2 atoms. So the summary here is that every carbon will need 4 lines, okay, aka octet. Now, having said that, let's go ahead and look at this red carbon I just re-highlighted up in this structure here. It is already bonded with 1 other carbon, right? That's what that line means. So how many, and the hydrogens are not drawn in explicitly, not all the time. Most of the time it is not. So you have to understand from this drawing how many hydrogens are attached to that carbon. So let's think that again. That red carbon is attached to 1 other carbon, the green one. So how many more hydrogens is attached to it that is not explicitly shown?
3.
Exactly, 3, because we know it has 4 bonds, right? If 1 is with carbon, the other 3 must be with hydrogens. Okay, very good. Let's apply that again. Now let's go over to the green carbon now. Can you tell me how many hidden hydrogens does it have?
1.
1.
Nope. Think again. Count. How many bonds does it have already?
2.
Well, let
4.
me draw. Yes, it has 4. Let me draw you the bonds, right? This green carbon here has this bond, this bond, this is a bond, and this is a bond, right? So it has already 4 bonds. So how many more hydrogens does it have?
None.
None. Very good. So that green carbon has no connection to any more hydrogens. Pause there. Any questions on that?
So the chlorine counts, the one with the dash one counts, and then the other one?
Mm-hmm. So if it's a line, it's a bond. If it's a wedge, it's a bond. And if it's a dash, it's also a bond. Those are all representative of single bonds.
And how come the dash isn't a hydrogen?
How come the dash? Oh, so the dash, remember the dash is just like any line segment. And what's the end of any line segment?
Carbon.
Carbons. Very good. So I'm going to go there next. So we just said that was a carbon, right?
Uh-huh.
So how many hydrogens is attached to that carbon?
3.
Very good, because it has a green attachment, right? It's connected to that green carbon and nothing else. So it needs 3 more hydrogens. Okay, let's do it some more. Let's do all of them. Now I'm gonna highlight that one yellow. Go ahead and count how many bonds it has already. And then deduce from that how many hydrogens it should have.
1.
Very good. It would have 1 more hydrogen. Good?
Yes.
Okay, so let's keep on going so we can answer this question. This is a, oops, where's my pen? This is another carbon, right? Go ahead. How many hydrogens is in that carbon?
3.
Yes.
3 more.
Very good. How about this one right here?
Which one? The blue or the red?
The red one right here.
3.
Very good. Okay, one more, right? We got one more to do. Let's just make it blue since we haven't used that color yet. This blue one right here, how many hydrogens?
2.
Very good, because it has 1, 2 bonds, so therefore 2 more hydrogens need to be bonded to it. Okay, very good. Notice I kind of color coded. All the reds are all the same. All the blues are the same. The yellows are the same, and the green, I mean, not the same, different. Okay, now all we have to do is count up all those hydrogens. Go ahead and count. 1, 2, 3, 4 times 3 is 12, 13, 14, 15. Did you get 15?
Yeah.
Okay, I got 15 too. Hopefully we were good. And then lastly, what's the last atom? We always do carbons first, then hydrogens, and then anything else we put in alphabetical order. In this case, there's only one thing after that, and that's chlorine. How many chlorines do we have? Just 1. Right? So what's our answer then? C7H15Cl would be A. One last thing I failed to mention here is what does it mean? What does the dash and the wedge mean? We talked about this already in lab when we did the covalent bonding lab. A wedge, just like in art class, something that's getting darker is coming towards you. Something that's getting lighter, for perspective-wise, is going away from you. So when I draw in that wedge, or when it's drawing the wedge there, it just means a single bond that's coming towards you. And a wedge is another single bond that's going away from you. Okay. All right, so questions on skeletal structures. Number 3, what is the IUPAC name for the following hydrocarbons? Oh, okay. It's similar to number 1, but in this case, is a structure is given to you. In this structure, we have shown here 1, 2, 3, 4, 5 carbons. Notice that the carbons at the end will have 3 hydrogens, and the carbons in the center, if they are not branched, will have 2 hydrogens, again, following the octet rule. Because it is 5 carbons and it's just a long chain without any branching, what do we call 5? Pent, right? So the answer is D, pentane. Number 4, which is the structure of the following compound? Okay, so this time I give you the name, and then your job is to draw out this structure. Okay, so in this one is a branched one. That's why the name is now no longer such a simple alkane, but it's a substituted alkane. So we just look at the parent name first. The parent name is hex. What does hex mean again?
6.
Right, so 6. So I draw zigzag with 6 corners, or 6, yeah. And then I just, because I'm drawing it, it doesn't matter which direction I call number 1. I'm just going to call the left number 1, 2, 3, 4, 5, and 6. That means at the second carbon, And the fourth carbon, I will have a methyl group. So a methyl group would look like that at the second and the fourth carbon. So among these, which one would qualify? Notice this one has a methyl group, but they're all at the same carbon. 1, 2 at the third carbon, right? So it's not this guy. Oh, B, 1, 2, 3, 4, 5, 6. Okay, it's 6. And is it at the second and the fourth? It is at the second and the fourth. So B could be an answer. B is definitely the answer, right? But just double check. Let's go on and check out the other ones. C, what's your longest chain? It'll be 4, right? So it would not be called a hexane. Whereas in D, 1, 2, 3, 4, 5, 6, 7. The longest chain is 7, so it wouldn't be called a hexane either. And then E is a cyclic compound, but the name didn't have any cyclic in it. So that's not the answer either. Yep, so the answer there is B. Notice that when we draw the structure, it can be in any orientation, any angle. It doesn't have to be the same that we drew it kind of like horizontal like that. Because molecules are free to rotate and tumble, so they actually don't. They're just not always the way we draw them, but they have the same connectivity. That's why the name, if you can name both molecules the same name, they must be the same molecule. That's one way to check them, except if there are stereoisomers, which we'll cover in a bit. Okay, any questions on naming or even drawing the molecule here? Of course, number 5 is another naming problem, so we'll go to that soon. Okay, let's just number 5 and see if I have any more questions for nomenclature. Okay. So the tricky part about naming a name, if you're just given a structure, is you have to follow the steps that's provided for you in naming names, right? The first step is finding the longest chain, right? Meaning that if you can trace the carbons without lifting up your pencil, how far can you go? That will be your longest chain. Okay, so for example, if I started here, 2, 3, 4, right? Then I can't go any more after 4, then that means my longest chain is 4. So you want to do that to find your longest chain possible. So let's say that was our first attempt. Let's do 1, 2, 3, 4, 5. Okay, so 5 beats 4. But maybe there's an even a longer one. 1, 2, 3, 4, 5, 6. Okay, 6 beats 5. Are we satisfied yet? Well, if not, just keep on going. We don't have to start at the same place every single time. Why don't we start here? 1, 2, 3, 4, 5. No, that's not longer, right? So indeed, 6 carbon is your longest chain. All right, what's after finding the longest chain? Every chain has 2 ends, right? The beginning and the end. So you have to figure out what is your beginning. And how do you choose what is your beginning? Your beginning on that path is a path that is where you see the substituent, the branching off, the earliest. Okay, so let's go there. Go ahead and just erase all of that for clarity. So remember our longest chain was this one. So this is an end and this is an end. So if I were to go from the left-hand side, 1, 2, 3, 4, 5, 6, I see my substituent first at number 3. Now, if I go from the right-hand side,
4.
1, 2, 3, 4, 5, 6, I see my first substituent at number
3.
3 again, okay? So it's a tie, right? So if it's a tie, then you keep on going. When do I see my second substitution in blue? I see it at
4.
Where do I see my second substituent in green? I see it as
4.
4. Turns out this is a total tie, and therefore it doesn't matter. But sometimes there will be a tiebreaker, then you just choose the one that won. Okay, in this case, it doesn't matter. So it doesn't matter where you numbered from the left or numbered it from the right. Okay. And then you can prove it yourself, because if you numbered from the left and you name it, and then you numbered from the right and then you name it, they are the same name. Like I said earlier, anytime you have the same name, they must be the same molecule. Okay, so let's now name it. Well, first thing we have to know is what's the name of the substituent? What do we call this substituent? How many carbon does it have?
1.
1 carbon, very good. If it's 1 carbon, we call it
Methyl.
So that would be called a methyl. And I'm just gonna go with the green in this case. And that methyl is on number 3, so I'm just call it a 3-methyl. What about what else? What about this guy down here? What will we call it?
4.
4
Methyl.
4-methyl also. Okay. All right. I'm just kind of just laying it all out there. So we know we have all our parts now. We just have to assemble it in alphabetical order. In this case, there's only methyls, so there's no real alphabetization to be done. Okay, so we just say, and because they're both methyls, it's repetitive to say 3-methyl, 4-methyl. So there's a short way of doing that. We would just say 3, 4. The 3s and the 3 and the 4 are locants, telling us the address of where the methyls are. And then next, because there's 2 methyls,
I.
how do we say di? We should say di. Okay, again, the 3 and the 4 tells you where each of the methyl, what's their location, what's their address. Okay,
Hexane.
so one time.
Hexane.
Hexane, that's the parent name. Very good. So you ended with the parent name. So this molecule is 3, 4 dash dimethylhexane. 3, 4 dimethylhexane would be D. Okay, any questions though before I move on to the second page?
So you said when you are trying to number them, you have to figure out like where the closest substituent is. Okay. And it'll be wrong if it's the opposite.
Right, let me give you an example then. 1, 2, 3, 4, 5, 6. Let's go with a simple example here, right? Notice your longest chain is 6. Right? You can number this from the left, being this as number 1, 2, 3, 4, 5, and 6. So your methyl substituent is on the 5th carbon. So you could have called this 5-methyl hexane. Yeah, but that's not correct, because if you numbered it from the right, 1, 2, 3, 4, 5, 6, that substituent comes off of the 2nd carbon. So its true name is 2-methyl hexane. You see the difference there?
Yeah.
So this is correct, and this one is incorrect.
Makes sense.
I can even add something. What it was, oops, dang it. How do I go back? Okay. What if I gave you that? Would you number it from the left, or would you number it from the right?
From the right.
From the left.
Ooh, from the right, actually. Why? Why from the left? Why from the right?
Because 2 is closer compared if you were to go from the left, it would be the fourth one.
Exactly. See, it doesn't matter what you see as long as you see something first. Whatever is giving you the lowest number will win.
What if there was one on number 2 on the left side?
Ah, giving even more complex one. Good job. Let's just do it. Dang it, I keep on doing that. Okay, this is a complex molecule now. What do people think? Do we want to number it from the left or should we number it from the right?
3, 4, 5, 6.
The right.
That is correct. You will still number it from the right. And why is that? Let's see. Right? If you number it, oops, wrong color. If you number from the left, you see the methyl group at number 2, right? So that's great. So you would see the methyl group at number 2, number 4, and number 5. Everyone in agreement if you did this from the red?
Yes.
If you did it from the right-hand side, which is color-coded green, you will see a methyl group at number 2.
3 and 5.
At number 3, right? And at number
5.
5. Okay, so this is where the tiebreaker comes in. So they tie at number 2, right? So that just cancel each other out. Then you go to the next one. In this case, 3 is better than 4. So that's why from the right is the correct way.
Would you still have to write down the 2?
Yes, you still have to write down the 2, all right? So let's name it for reals. It's still a hexane, and then there's 2, 3, 5, right? Every single time a substituent appears, you have to give a locant to it.
How do we know?
Even though they're
substituent is?
Repeat?
How do we know what the substituent is for that one?
The longest chain is the parent chain. Anything that is not a part of the longest chain, we call substituent.
Okay.
All right, so even though all 3 substituents are identical, we still have to put 2, 3, 5, okay? But if they are identical, then we need a prefix telling us how many they are. It's a little bit redundant, but it's to make sure that the structure is right. Because if you give me 3 number, I know there's 3 of them, right? But I know it's redundant, but we're just gonna do it anyways. Trimethyl. And then lastly, the parent chain is still hexane. How's that? Any questions? Let's continue. All right, and then this is truly your last lecture. This is the last video you would have seen this whole semester. Yes, I believe so. Yep. Starting with number 6 here. What is the relationship between the following 2 molecules? Ooh, okay. So there are different relationships that you should know, right? The first one there is a structural isomers. The second one there is a stereoisomers. And then lastly, if they are identical to each other, okay? First off, let's count how many carbons and how many other atoms each molecule has. Because if they have a different number of atoms, then by definition, they don't have a relationship with each other. But if they have the same molecular formula, meaning they have the same number of atoms, then they will have these different relationships. Okay, so let's count this one here.
6.
2, 3, 4, 5, 6. C6, how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And Br. Whereas the right-hand guy has C6 also, but each one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It has only 11. There you go. They have different number of hydrogens. Because they have different number of hydrogens,
Totally different.
they are totally different molecules. Okay, so the answer is A. Now, let's just focus on the first one here to give us some examples. What would be a structure of something that is a constitutional isomer, or what do we call it? Structural isomer. These words mean the same thing. Maybe you've heard it in different contexts. Constitutional or structural isomers. Both of these isomers, iso means the same, right? So they have something in common. So they share the same molecular compound, meaning they have the same number of atoms. But what is different about them is the structure. And what that means is how they are connected, how the atoms are connected to each other. So for example, I can draw a molecule where the bromine is right here. Okay, so if you notice, this molecule has C6H13 and 1Br also. So they do have the same makeup, right? They have the same amount of atoms, but the way the atoms are connected are in a different order. Notice that this bromine here is connected to the second carbon, whereas this bromine on the top is connected to the third carbon, right? So the order of connectivity is different. So we would call that a structural isomer or a constitutional isomer. Okay. And then lastly, stereoisomer is kind of trickier. So let's take a look at this new molecule I drew in black here. Again, it is C6H13 and 1 bromine. Are the order in which the atoms connected the same? And it is actually, right? The carbon connected to carbon, carbon connected to carbon, and at that second carbon, there's a bromine. And the rest of the molecule is the same, right? So the connectivity is the same. But they are not the same molecule, right? Even though they're the order in which atoms are connected the same, it's just the spatial, the 3D ways they are connected are different. So for example, the original molecule has bromine coming towards me, and the new molecule that I drew has bromine going away from me. Because of that 3D differentness, and anything in 3D we call stereo. So these two molecules will be called stereoisomers. Okay. I don't have a model kit in front of me right now, but we can prove that to you when we do the lab, when we build molecules in the lab and see if they are identical molecules. Because if they are identical molecules, when you put them close to each other, they will merge and disappear into one another. But for the two stereoisomers I drew right here with the bromine, they can never merge and overlay. Because if you merge them, notice that here, can you do a mental merging? Okay. If we were to overlay all the carbons I have highlighted in red, they will disappear into each other, right? Can you kind of imagine that? But once all the carbons are merged to each other, will the bromines merge into one another? No, right? Because one bromine is pointing that way and the other bromine is pointing that way. Because of that, they're actually different molecules from each other. That's called stereoisomer. Another form of stereoisomer is called a cis and a trans, which is actually the second problem we'll see in a bit. Let's do an example of a cis and a trans stereoisomers. So for example, let me just put it down here. Right? This is what we call a cis, and this is what we call a trans. Cis means same side, trans means opposite side. Notice that the molecule has the same, notice that both of these molecules have the same formula, which is C1, 2, 3, 4, H1, 2, 3, 4, 5, 6, 7, 8. that right? 1, 2, 3, 6, 2, 8. Okay. They both have the same formula. And are they connected in the same order? They are, right? A carbon connected to carbon, another carbon, almost in a straight line, right? The right hand is also a carbon connected to 3 other carbons in a straight line. So the order in which they are connected are exactly the same, but they are very different molecules, right? One has the methyl groups pointed down. The other one has the methyl groups pointed in opposite phase. That's why they call it cis versus trans, same phase versus opposite phase. Because of this, they are called stereoisomers. So this is another example that we learn in this class. Oh no. Oh, what happened? It's gone. I can't undo that. Anyways, so that was the cis and trans isomers, because again, they have the same connectivity, they have the same chemical formula, but they do not merge because of their 3D spatial arrangement. Okay, so that was a long discussion for number 6, but a good one too. That will help you a lot with your homework today. So that kind of segue to our number 7. It says, observe the following alkene molecule, and then identify the cis and the trans bond that we have in the double bonds. Okay, so let's take a look at it. Okay, so this is your first double bond. Just noticed the carbons are coming off of them. Are they going in the same direction or opposite direction? If they are opposite, we call it trans, right? So that's a trans. And if they are the same, notice, let's do a different color for clarity. This is a double bond. Are the carbons coming off of it in the same direction or opposite direction? This way and this way, right? So the same, so we call that cis. And lastly, this one, number 3, what do we call that? Trans. So the answer there would be trans cis trans. Trans cis trans. Answer there would be C. All right, pausing there. Questions for relationships, structural stereoisomers. Any questions?
What would a cis trans look like for D?
Cis, trans, trans? Well, cis, trans, trans. Does that
Yeah.
look like a cis, trans, trans to you?
Yeah.
Yeah.
Okay, thank you.
So just figuring out where the carbons are to each other. Yeah, like cis and trans, even though they are very similar to each other because they have the same molecular formula and they have the same connectivity, the 3D arrangement is different, can make a big difference. Like we know cis fat and trans fat, right? When we look at food labels, one is okay for us and one's really bad for us, right? So even though they may be exactly the same in every way, but the cis and the trans will have different biochemical properties. Okay. Number 8, what property? So number 8 is more of a kind of just kind of knowing facts about hydrocarbons, right? All right, so what property is not typical of hydrocarbon compounds? Okay, so again, just to clarify what hydrocarbons are, hydrocarbons mean a compound that only has carbon bonds and carbon-hydrogen bonds. If they only are carbon bonds and carbon-hydrogen bonds, all their bonds are what? Non-polar, right? If all of their bonds are non-polar, that means the molecule is what?
Non-polar.
Also non-polar. Very good. So we can get rid of D already. So we know that is true. all hydrocarbons are indeed nonpolar molecules. Now, let's kind of see what kind of characteristics of a nonpolar molecule. Like in letter A, it says insoluble in water. Water is polar, right? So will these, will water mix with something which is polar, will mix with something that is non-polar?
No.
They will not mix. If something doesn't mix well, it doesn't dissolve in it, we call that not soluble in it, right? So indeed, A is true. So A is not an answer. So water and hydrocarbons will be insoluble. Okay, let's go with B, C, and E. Oh, C, mostly covalent bonds. Oh, that's a tricky one. Mostly covalent bonds. What do you think? If you don't know, let's just continue with B and E. Are hydrocarbons combustible? What does combustible means? They will react with oxygen in a combustion reaction, right? And actually, that is the definition of a combustion reaction. So yes, they are combustible, but that's not an answer. That's a fact. Let's go to E. Will they conduct electricity? Hydrocarbons conduct electricity. What do you need to conduct electricity? Some kind of ions floating around or electrons floating around, right? So no, they will not be conducting electricity. So E is not true. So the answer would be E. I was hesitant with C because it says mostly covalent bonds. Actually, they're all covalent bonds. But maybe there are some exceptions that we don't learn in this class. Yeah, so that's why C was kind of tricky. But even though we don't know C, we know that E must have been false. So E was definitely the answer. Okay, questions on 8, knowing its properties and stuff like that. And I kind of mentioned it at the beginning of the talk today, or of the session today. Another property it has is the lower the number of carbons it has, and the less London dispersion forces, therefore the lower the boiling point and melting point. So it's gas in lower carbons, middle carbons would be liquids, and higher carbons would be solid. And if you get really, really, really high carbons, we just get plastic, right? So that's really, really hard solids. Because at that stage, it's just many carbons connected to each other in something we call polymer. Poly for many. Okay, let's finish this off. So the last part of this lecture is basically identifying and kind of knowing functional groups. And functional groups are basically features of a organic molecule depending on the atoms it has, and we group them in a family. Because they have these kind of motifs, these patterns, they will react in the same way. So it's good for us to kind of group them together so that when we study its reactivity, we can say, okay, this group of molecules, this family, they tend to do this. This other group of family, they tend to do this when you add, X, Y, Z. Okay, so that's why we need to be able to identify these groups, these patterns, these families, what we call them functional groups. Okay, so in this number 9 here, what do we notice in this molecule? I'm going to highlight in yellow one functional group. Anytime you see a carbon connected doubly to an oxygen, first off, in general, that's called a carbonyl. Okay, anytime a carbon is doubly connected to an oxygen, we call that a carbonyl. Now, off of that carbon, depends on what comes off of it, this carbonyl will have subfamilies, more functional groups. If there are both carbons that are coming off that carbon, what do we call it?
Hydrocarbon?
Close. Okay, so this section, folks, the best way to study this section is to make flashcards. Okay, hydrocarbons is just a generic term for any carbon hydrogen containing molecules. So not hydrocarbon. Hydrocarbon is not actually a functional, it's not a functional group. There are many different functional groups in hydrocarbons, for example. So the name is
Ketone.
yes, ketones. If you go on a keto diet, you will pee out a lot of ketones. That similar idea, name-wise. So yes, that functional group is called ketone. What's the other functional group here? Let me highlight it in green. So that is another functional group. This is actually a hydrocarbon functional group, but more specifically, what is its name? Anybody?
Aldehyde.
Ooh, no, actually, an aldehyde is a C double O functional group, the carbonyl group. So it's not an aldehyde. It's close.
Alkane.
Yes, alkene. So the answer here is ketone and alkene, D. Let me draw you what an aldehyde looks like. This is what an aldehyde looks like. See that functional group, that carbonyl functional group? Right, we still have a carbonyl functional group there. So it is still considered a carbonyl. It's still a carbonyl. Remember, a carbonyl is just a bigger family. But specifically, when that carbonyl has a hydrogen instead of a carbon connected to it, we call it an aldehyde. Okay, so that connection is a difference.
So it's when that it's connected to a height. Okay.
Yep, exactly. Like when you change that, let's say, since we're here, might as well review. See, another carbonyl, but let's say you're connected now to an OH. It has a different name now. It's still a carbonyl, but this is now called a carboxylic acid. Okay. Now, let's say we have an oxygen, but this time not a hydrogen, but another carbon of any length, maybe 1 carbon, 2 carbons, 3 carbons, 4, whatever, doesn't matter. Anytime you have a carbonyl with an oxygen and then another carbon, we have another name for it. Anyone remember? Starts with an E.
Ether.
No, close. Ester. Yeah. Okay, this is an ether. Okay, an oxygen with carbons on both sides, but no carbonyls. You see that? So that's an ether. I can give you endless examples of this. Come to office hours. Okay, again, kind of just look at the patterns, recognize it. These, again, I consider easy points, folks, easy points. If you just, take some time to understand them and practice with them. Okay, so on the same line of thought here, the number 10, what functional groups is not found in this molecule? An oral contraceptive. So let's go ahead and highlight some functional groups. Okay, I'm going to first highlight functional groups for you. You should be able to do that on your own, but I'm going to highlight them for you first since we're like probably new to this. And then I'm going to give you some time to kind of name each one. That's one functional group. That's another. That's another. And then that's another. So we got 4 functional groups. Notice the carbons in the center I didn't highlight because they're just boring hydrocarbons. They don't actually have a functional group. Actually, you could call them a functional group, but they're not exciting. So they're just alkanes. So we just want to highlight the ones that are a little more exciting. Those 4 right there. Anyone want to shout out what you can recognize?
The green, is that ether?
Yes, very good. That one would be ether because of the oxygen connected to two random carbons, no carbonyls. And then Karen, you said aromatic. Okay. Can someone say which one's the aromatic? Aromatic is indeed in here. What color? Very good. This is the blue is aromatic. So how do you recognize aromatic? Anytime you see a cyclic compound with alternating single double bond, that's aromatic. It does get more complicated than that, but in this class, we're going to simplify it and call that aromatic. Very good. More straightforward. How about the yellow one? That's a straightforward one. What do you think the yellow one is? Something you drink? Maybe? Yes, that's alcohol. Okay. It's called alcohol because one of the simplest alcohol out there is this alcohol. Does anyone know what this alcohol is? This is the actual alcohol molecule that you drink when you consume alcohol, when you consume like beer or wine or whatnot. That's the molecule. Very simple, 2 carbon, and then this OH group. We call this ethanol, right? So different composition of ethanol with water is what we call, wine or beer. And, of course, there's other flavor molecules in there, but that's the extent of it. Lastly, what is Mr. Red? Red is, it's a carbon-carbon triple bond. What do we call that?
Triple bond. Alkyne.
Yes, it has all kinds of fun. Okay, that's how you remember that, alkyne. So yep, a carbon-carbon triple bond is called an alkyne. Okay, so the answer would be
C.
Right? You don't see an alkene. This is what's tricky, right? Some people say, isn't that an alkene? Because an alkene is a carbon-carbon double bond. So maybe people might say that that's an alkene. So when an alkene is in a cyclic ring and it's like double, single, double, single, in a pattern like that, it's no longer considered an alkene because it's now considered an aromatic instead. Okay, so the bigger functional groups defines it more than a smaller one. So for example, if this, well, that doesn't make sense. Wait up. If this was a double bond, then that would be considered an alkene. Okay, just because it's just by itself. It wasn't alternating with anything.
So because there's 3 double bonds, that's what makes it aromatic. So you're saying if it was only 1 double bond, or
That's right. That's right.
okay.
Yeah, like I just drew out that new one right there. That one is it's a ring and it's only 1 double bond, so we still call it an alkene, right? Or even this. Sorry. Right? If I drew that, then there would be 2 alkenes, right? But as soon as I draw in the third one, which by the way doesn't exist for other reasons, I can explain why it doesn't exist in a bit. But let's just say if I did draw in that third one, then automatically will no longer be an alkene. It will be a benzene instead, or I'm sorry, an aromatic instead. You don't know benzene.
Okay, so
Aromatic.
alkene up to 2 double bonds.
One more time.
So alkene in like this scenario would only go up to 2 double bonds because if it went to be aromatic. Okay, sorry,
Yep.
just thank you.
Okay. Follow-up question. Does anyone recognize why I can't draw that double bond there, that last one? Why can't I draw that last double bond? Trick question. Not tricky. It relates to something we learned like at the beginning of the day today. And I want you to focus on this carbon right here.
It'll be too many hydrogens or too many carbons.
Too many what? You're getting there. Too many
Bonds.
Yes, very good. Too many bonds, right? That'd be 1, 2, 3, 4, 5 bonds. What's 5 times 2? 10, right? A carbon cannot have 10 electrons connected to it. So that's why I keep on drawing that by accident. And then say to myself, nope, that's not possible. But yeah, because every carbon maximum of 4 bonds, so that cannot be. So yeah, so this doesn't exist. Cool. Kind of a review question there. Okay, very good. So that ends our discussion on the organic chapter, the quiz part at least. I'm gonna go ahead and stop the recording. Is that okay? And then you can ask me questions. Bye.